Hey everyone, in this AP Chem series video, we'll take a look at some of the attractive forces that play a role in solutions. So remember that we've already seen a whole list of intermolecular forces and talked about most of them, but there's two we haven't gone into yet. That's the ion dipole force and dipole-induced dipole force. This video is going to go into greater detail on both of these. Let's start with ion dipole forces. These are attractions that exist between ions and polar molecules, like you can see here, between the sodium and chloride ions and water molecules that surround them. Here's some things to notice about these models. First of all, the cation in purple is positive, so it's attracted to the partially negative end of the molecule. The green anion is negative, so it's attracted to the partially positive end of the molecule. Also notice that there's multiple molecules surrounding each ion. That's common for this type of attraction, especially when it comes to solution formation. In terms of relative strength, these ion dipole forces are stronger than the other intermolecular forces. Make sure to take some time and write down these key ideas. Sometimes you also have to compare the strength of one ion dipole force to another, and you can do that using a lot of the same principles we've seen with the other intermolecular forces. Ion dipole forces are going to be stronger in three scenarios. One of them is smaller ions. The other one is ions with greater charge magnitudes, and the last one is greater net dipoles on the molecules. This model shows the ion dipole forces that might form between sodium and magnesium cations and some water molecules. Since the magnesium ion has a +2 charge, that means it has a greater charge magnitude than the sodium does. It also happens to be a smaller cation. Both of those things suggest that the attractive force between magnesium and the water molecules will be stronger than the attractive forces between sodium and the water molecules. Here's a different model. This time we're looking at the ion dipole forces between sodium and water and sodium and hydrogen fluoride. Since both scenarios involve a sodium cation, that's not the difference between the two. Instead, we have to look at which of the two molecules has the greater net dipole. There's a very large electronegativity difference between hydrogen and fluorine. That means the HF molecule is more polar or has a greater net dipole. This tells me that the ion dipole force between sodium and hydrogen fluoride will be stronger than those between water and sodium. Make sure to take some time and write down the key ideas related to comparing ion dipole strength. We've also got dipole-induced dipole forces. These are attractions between polar and nonpolar molecules. What happens is a polar molecule can actually cause a nonpolar molecule to become temporarily polarized, a lot like we saw with London dispersion forces. Let's see how this works by looking at water, a polar molecule, and Br2 bromine, a nonpolar molecule. Notice the even distribution of electrons around my nonpolar bromine. If the partial negative end of the water molecule shown here near the oxygen gets near this electron cloud of bromine, it's going to cause that electron cloud to shift more to one side since the negative charges repel each other. Now that all of the electrons have shifted over to the right-hand side of the molecule, I have a molecule that used to be nonpolar, but now there's a partial positive on the left and a partial negative on the right. The molecule has become temporarily polarized, or we could say that a dipole has been induced. The final result is that the partially negative oxygen in my water molecule is now pointed towards the induced partial positive on the bromine, and the two molecules will be temporarily attracted to each other. That attraction is called a dipole-induced dipole. Make sure to take some time and write down these key ideas related to dipole-induced dipole forces. These attractive forces are generally weak compared to most of the other IMFs, but they can be stronger in a couple of scenarios. One of those is if the polar molecule has a greater net dipole, and again, you can test that by looking for greater differences in electronegativity. The other time you'll see stronger dipole-induced dipoles is if the nonpolar molecule is more polarizable. This happens when there's more electrons or a larger electron cloud. Let's compare the dipole-induced dipole forces between water and bromine and water and iodine. Since bromine has a smaller electron cloud, it is less polarizable, and that dipole-induced dipole force will be weaker. On the flip side, iodine has a very large electron cloud, so it's very polarizable, resulting in a stronger dipole-induced dipole force. Here's a different example involving water molecules and hydrogen fluoride molecules both being attracted to bromine. Like we saw earlier, there's a smaller difference in electronegativity between oxygen and hydrogen atoms, so the water molecules have a smaller net dipole. That means the dipole-induced dipole force here is going to be weaker. Hydrogen fluoride has a greater net dipole because the electronegativity difference between H and F is greater. That's going to result in stronger dipole-induced dipole forces between HF and bromine. Make sure to take some time and write down these key ideas related to comparing dipole-induced dipole strength. That also concludes this video. Thanks a lot for watching, and here is a brief summary.